Okay, so today we're going to be graphing this inequality that's a quadratic inequality. We've got y is less than x squared minus 4x plus 3. We're going to use the same process to do our boundary parabola that we did when we had regular quadratic equations. So the first thing I'm going to do is I'm going to find my y-intercept. This is a good reminder for those of you that are having trouble with graphing quadratics of what you need to do. The y-intercept is what you get when x is 0. So if I plug 0 into my equation, because remember when we're doing our boundary, we treat it as though it's an equation. So if I were to plug this into the equation, y is equal to x squared, so that'd be 0 squared minus 4 times 0 plus 3, I would just get 3. So there is my first point. My y-intercept is at the y-axis at 3. Next, I'm going to find my x-intercepts, and again, I'm going to pretend like this is an equation, and I'm going to be solving this equation, y equals x squared minus 4x plus 3, except instead of y, since I'm looking for an x-intercept, it's going to be 0. I can factor this, so I'm going to do my area model and my diamond, and I'm going to get x squared and 3. 3x squared goes in the top of my diamond, negative 4x goes in the bottom. Two numbers that multiply to a positive but add to a negative both have to be negative. So my options are only negative 3x and negative 1x, which does work. So then I can fill in the outside of my diamond to get my factored form. Factored form is x minus 3 times x minus 1. That means either x minus 3 equals 0, in which case x is 3. So there's one of my x-intercepts, 3, 0. Or x minus 1 equals 0, in which case x is 1. So there's my other x-intercept, 1, 0. So I go ahead and I plot those on my graph over here. 1, 2, 3. The vertex is always halfway in between the x's. Halfway between 1 and 3 is 2. So I know my x of my vertex is going to be 2. I can plug 2 in for x to my equation to find the vertex. So I'd have 2 squared minus 4 times 2 plus 3. So this is 4 minus 8 plus 3. 4 minus 8 is negative 4 plus 3 is a negative 1. So my vertex is the point 2, comma, negative 1. So that is enough for me to graph my boundary. Now I need to figure out, is my boundary going to be solid or dotted? And if I look at the symbol in my original problem, I see that it is just less than, so that means it's going to be a dashed parabola. So I'm going to draw that dashed parabola. And again, when we're doing parabolas, they're just sketches. And if you forget that it was supposed to be dashed and you draw your parabola and it's solid, you can always write the word dashed next to it to let me know that you wanted it to be dashed. Okay, now I need to figure out, am I going to be shading inside my parabola or outside my parabola? The way to do that is to pick a test point. The easiest test point is always 0, 0. And as long as 0, 0 is not on your boundary parabola, you can use 0, 0 as a test point. If I look at my parabola, 0, 0 is not on it, so I can use that as my test point. So I am going to now show all my work. So my test point is going to be 0, 0. I'm going to plug 0, 0 into my inequality, and I'm going to see, is 0 less than 0 squared minus 4 times 0 plus 3. When I evaluate all of this, I get 0 on the left side. 0 minus 0 plus 3. Is 0 less than 3? Yes. That means that 0, 0 is a solution. So my final step is going to be to shade where all of the solutions are. Since 0, 0 is a solution and it's outside of my parabola, I am going to shade this entire outside portion of my graph. Everything inside the parabola does not work with this inequality, so they are not solutions. Everything outside the parabola does work, so those are solutions. And you can use the same process for any function, whether it's a quadratic function where you get a parabola, or an exponential function where you would get a exponential curve. The biggest thing is, remember, your boundary is either going to be shaded, it's going to be dashed or solid based on what the symbol is. Pick a test point. Use 0, 0 if you can, and you can use it as long as it's not on the boundary itself. And then your test point tells you where the solutions are if it works, or where the non-solutions are if it doesn't work.